Hey, this is Mel Strong, and in this lecture we're going to talk about seasonal changes that occur in Earth's atmospheric circulation pattern. So, we're making the transition from weather to climate, and we haven't really talked about the difference between weather and climate yet, so we're going to start with that. So weather is what we've been talking about so far in this class. It's what's happening right now in the atmosphere. It's the current conditions, okay? Now, weather, turns out, you can't really predict it more than about 5 days out, and we probably never will. And the reason for that is something called chaos that's in the atmosphere. Now, chaos is a mathematical thing, but you can kind of think of it as if you have a system that's so complicated that there are too many variables. We call those degrees of freedom, and all these extra degrees of freedom mean that you can't really make predictions very far out in time. So what will happen is a very small change somewhere in the atmosphere can propagate to a much bigger change that's unforeseeable a few days in the future. Mathematically, it's a pretty complicated thing, but you can kind of get a sense of it with this movie that we saw before. So this is water vapor in the atmosphere, and the bright white are clouds. And so if I took a freeze frame of this, right, and I asked you, okay, based on all the swirls and everything you see, what would this look like, say, 5 days in the future? It's nearly impossible to do, okay? There's so much going on here. There's a lot of chaos. And so that means it's really impossible to predict out more than 5 days. Some outlets, let's just say, I don't know, the Weather Channel, will claim that they can make predictions beyond, they do a 10-day forecast. But if you keep track of how well they're doing in their 10-day forecast, it's actually pretty bad, okay? So realistically, 5, maybe 7 days. So that's weather. Climate. Climate really refers to the average conditions for a given place at a given time. So in other words, we might say, okay, what high temperature do we expect in Albuquerque on July 1st? So the answer to that, we would go back to all the July 1sts that we have on record and average the high temperatures, okay? That's climate. And it can include all kinds of things: the high temperature, the low temperature, the average temperature, the precipitation, the dew point. There's a lot of things that we can include in climate. Now, the weird thing is that climate is actually predictable for decades out. So it would be impossible for us to say exactly what's going to happen September 15th of next year in terms of the weather. We just can't do that. That's impossible. But what we can do is we can say 10 years or 20 years in the future, what will a average September month be like? How will it be compared to an average September this year, right? That's the kind of thing that we do with climate. So how is this possible? Well, there's one little analogy I do that might help. Imagine if you have a cigarette, and the cigarette's burning, and it has all these wispy curls of smoke that come up, right? And I take a picture of that, and I say, okay, tell me exactly where all these little smoke particles are going to be in 5 seconds from now. Okay, that would be very hard to do. There's too many degrees of freedom. It's too much chaos in this system. That's weather. Climate would be, okay, now we're going to take our cigarette, and my question is, where do you expect the smoke to be, say, 5 seconds from now? And climate would say, well, all the smoke is going to be contained in this volume right there. That's sort of the difference between weather and climate. Weather is concerned about where are the individual particles of smoke going to be. Climate is concerned with, well, where is all the smoke going to be contained? Sometimes we refer to this as the boundary conditions. So for any given place, there are limitations. Like it only gets so hot, it only gets so cold. There's only a certain amount of water vapor that you expect in the air. These are the boundary conditions, and they're set by all kinds of things like the atmospheric chemistry and the tilt of the Earth's axis and what the sun is doing, all these different things, okay? So that's climate. You can actually make a better prediction for climate decades out than you can with weather more than about a week out. There's another term that you will sometimes hear called a climate normal, or sometimes we just say a climate norm. Climate normal is climate data for a 30-year period. And it came about because a long time ago, there was a bunch of scientists at a weather meeting, and really reliable weather stations had only been around for about 30 years. And so they decided to use a 30-year chunk of time to represent climate. And every so many years, they redefine that 30-year chunk. So sometimes when you look up climate conditions for a certain place, like back to my example, what's the average high temperature for July 1st in Albuquerque? It usually, the number you might find if you look something like that up, will come from a 30-year chunk of time called a climate normal. Okay, so we'll see these in this class. Okay, first things first. Why do we have seasons? So if you ask a lot of people, including college graduates, why is it warmer in the summer and colder in the winter? The most common wrong answer that you will get is that the Earth is closer to the sun in the summer and farther from the sun in the winter. And kids believe this, adults believe this, Yale graduates believe this. Okay, so let's just go over this first. The reason we have seasons is because the Earth is on the tilted axis. Now, this orbit looks like an ellipse, but it's actually pretty close to a circle. Now, if we move around the sun, okay, with time, so let's say here I am in June, and what you can see is that if you lived up above this little red circle, the Arctic Circle, that you are in sun 24 hours a day, right? And if you live somewhere down here, you have part of your day as sun, part of your day as night. And if you're down here, which we can't see right now, they're in the dark 24 hours a day. So I'm going to show that. Okay, this is just another view of the same thing. Here's these guys down here in Antarctica. They aren't seeing any sun whatsoever, right? So right now, the northern hemisphere is getting more sun. Southern hemisphere is getting less sun. Okay, so it's our summer and it's their winter. All right, so if we travel forward in time, we come around, and as we go around the sun, we're maintaining this tilted angle, right? The angle of rotation of the Earth's axis, it's not exactly perpendicular to the plane that it orbits. It's tilted a little bit, about 23 degrees. And that's why this is happening. So if I come over here, now we're in the winter, our winter, and you can see that the guys that are in the Arctic Circle and any place north of that are in the dark 24 hours a day. And if we can see what our friends in Antarctica are doing, they are in the sun 24 hours a day. So our winter, their summer, okay? But it's not the distance, right? In fact, in the northern hemisphere, our summer, we're actually farthest from the sun in the summer. And we're actually closest to the sun in the winter for us in the northern hemisphere. All right, so with that, let's talk about what the seasons actually do. As a result of this tilted Earth's axis business, we alternate between heating the northern hemisphere and then heating the southern hemisphere, right? So here's a little animation. It says net shortwave radiation. That's a kind of a fancy way of just saying sunlight. So just imagine that this is showing you how much sunlight hits the ground as the months go by, okay? And you see there's this band of dark red, which is the most intense sunlight, and it migrates north and it migrates south with the seasons. Now, it's not a perfect band. It's kind of splotchy because it also takes into account clouds. So this is how much radiation actually hits the surface, which if there's a lot of clouds, it will reflect some of that. So that's why it's not a perfect band. But a couple things to think about here. First of all, when we have the winter up here, right? They have the summer down there. Okay, hopefully you know that, but some people don't. what would life be like if you lived right out here, say where my dot is right now? So this would be kind of weird because the red band passes you over there and you have summer, and then it comes back down and passes you again and you have summer again. So if you lived along the ITCZ, that area, you actually would have 2 summers. You don't really have anything you could consider winter, or even seasons for that matter, but you have 2 extra hot periods of the year if you live near the equator. Well, if the Earth was all the same thing, then the patterns of temperature would kind of follow that last animation. But it's not all the same thing. And so this, what we're looking at here, is air temperature, again, throughout the months. And you can see that there's a band here of high air temperatures, and then you can see the blue, purple colors are the cold temperatures. So a couple things to notice. When it becomes the winter, say our winter, the continents cool off much quicker than the oceans, right? So you can see that. And in the summer, the continents heat up faster than the oceans. So we talk about sometimes this term heat capacity, that it takes a lot of energy to heat up water, and then once water is warm, it takes a long time for it to cool off, whereas soil heats up pretty quickly, cools off pretty quickly. So the temperatures of the continents change much more rapidly than the temperatures of the oceans. So that's one thing to notice. Another thing to notice is that really, if we're thinking about the ITCZ, so again, this is a continuation of the last lecture. So if you didn't watch the last one, go back and do that first, or nothing's going to make sense here. The ITCZ follows the hottest part of the Earth, okay? But the hottest part of the Earth is moving, right? So if you imagine kind of right in the middle of this orange blob, kind of right up through North Africa, down here, right? So as you watch this, the ITCZ is going to follow the hottest part of the Earth. So it's also moving with this orange blob here. So as the seasons change, the location of the ITCZ changes. Well, remember at the ITCZ, that's where air rises, okay? Well, if you change where air rises, then you're also going to change where the air comes and sinks back down. So where it's not shown here, but we'll see in a second, is the locations of the subtropical highs also change with the seasons. So what we're getting into is a pattern, many patterns here that are going to be shifting with the seasons. The ITCZ, the Hadley cells, subtropical highs, polar fronts, easterlies, westerlies, all that stuff, it's all going to shift with the seasons as we alternatively warm and cool different parts of the Earth. Okay, so here is an animation that kind of shows how some of these things change with the seasons. So right now I've got a time slider down here and it's set early January. And I can see that the ITCZ is this purple line right here. And the first thing you'll notice is that it's actually not a straight line. And if you remember from the previous lecture, we looked at some diagrams from a textbook that showed the ITCZ is this nice, perfectly straight line, usually right at the equator. And we see that it hits the equator in a couple places here, but it's not at the equator. So right now we're in the winter. And so the winter is heating up the southern hemisphere more, which means that these continents down here are heating up more, which means that the warmest part of the Earth is kind of near the equator, but right now South America is warming up quite a bit because it's their summer. So you see it dip down to the south a little bit, then returns close to the equator. Then again, Africa is warming up because it's summer, and then it dips down again, and then it gets into some really warm ocean water, which we'll talk about probably in a couple lectures. Now, here it shows the Hadley cells. This is where the air is rising, and you can see they show the air moving to the north and the south and sinking down about 30 degrees north, 30 degrees south. And of course that travels all the way across, the world, right? So this is going all the way around the planet. They also show in here the polar front. Now this is kind of a weird way to show it because the polar front itself is a wavy line, kind of like the purple line, and it would be coming along kind of through here, right? and it changes day to day, right? It's always changing with a bunch of these Rossby waves. Okay, so I'm going to move forward in time, and so as I do so, we're getting into our spring, and then we're getting into our summer, and you notice how this whole thing is migrating northwards, right? And as it migrates northwards, the Hadley cells also migrate northwards, and polar front migrates more northwards. So I continue to move this. Oh, we just got past summer. Now we're going to get into fall, and you'll see the ITCZ moves back down. Down meaning south, right? Okay, so this is how the ITCZ changes with the seasons, and Hadley cells change with it, which means that where that air is coming down right here, that's where that subtropical high is going to be. It's also going to change. So I'm going to show pressure. That's what that button does. Okay, so let's see if we can figure out what's happening here. So I'm going to go back to January, and we've got our subtropical highs. There's a strong one right there, one right there, one right there, about 30 degrees, right? More or less 30 degrees. Then we've got some over here and here. Those are about 30 degrees. We also have some highs. If you remember back when we talked about air pressure, we said that you could get a high pressure if you have just really cold air. That's what's happening here. So our friends over here in Siberia, which are very cold, they're experiencing some high pressure just from a big pool of cold air, as our friends in the Northern Territories up here in Canada, very cold air makes a high pressure for a totally different reason. Also, we can see lows here and here. These are places where mid-latitude cyclones often form. We didn't talk about this when we talked about mid-latitude cyclones, but there's certain places on Earth where they happen to form over and over. The conditions are just right. And this is referred to as the Aleutian Low. So these are the Aleutian Islands. And it's just a place where these mid-latitudes start to spin up. And we talked about the stages that they go through. Well, they start here. So it's low because, on average, this is where you often get the warm fronts and the cold fronts over and over and over and over, right? You can get them other places, but if you average it out over many years, you would see it kind of, there's a low pressure that kind of hangs out over here and one over here. Okay. Also, one other thing, looks like we have a thermal low right here, so it's super hot in Africa. Hot air rises, so they put a low here. Okay, notice this one. This is the Pacific subtropical high. Okay, we've talked about this last time. It's sitting out here in the ocean. I'm going to go forward into time and notice what it in particular does. So as we go forward in time, our lows that we had up here from the mid-latitude cyclones are going away. They're still mid-latitude cyclones, but they're pretty weak and they're really far to the north. But notice what's happened to our Pacific subtropical high. It's getting bigger, which means it's getting stronger, but it's also moving away from the continent. Okay, so here we are in July, and we see it's kind of parked out here over the Pacific, and it's big, right? Let me go back. If I go back, in our winter, it's smaller, but it's actually much closer to us, meaning New Mexico, Southern California, Arizona, much closer to that area. And in the summer, it gets bigger, but it kind of moves further offshore. Okay, so this is important because what we're leading up to is we're trying to explain weather patterns, climate patterns that we see in the United States. So one of the climate patterns that we see in New Mexico and in Arizona and in Southern California is that we have pretty dry winters, right? In New Mexico, most of our precipitation falls in the monsoon season in the summer. And then the other half of it is scattered throughout the year. So we have pretty dry Januaries, pretty dry Decembers, pretty dry Februaries. And that's because this Pacific subtropical high is just sitting right out there, really close to us. So even though it's weaker, it's closer, and we feel the effects of that Pacific subtropical high. Now, in the summer, it gets bigger, it gets stronger, but it moves further away from us. So we get a relief from the Pacific subtropical high, and that is one of the things that allows our monsoon to actually kick in and start producing precipitation. But, and it's not too clear on this, but it actually is closer to the west coast up here, like California, Oregon, and Washington State. So their summers are actually going to be really, really dry because of this Pacific subtropical high. It sits out there right off the coast, and they are under the influence of sinking air day after day after day. So we can see this on earth.nullschool.net, and you can actually change the date and look at different times in the past. So what I've done here is I've loaded up a day that's in January, and we're looking at surface winds, and I'm actually going to change the overlay to MSLP for mean sea level pressure. And right there, spiraling off the west coast, so there's California, there's roughly the international border, and there's the Pacific subtropical high. It's spiraling around really pretty close to where we live, right? And you can see the winds coming right down the coast here. Now I'm gonna change. I'm gonna go one day further. Now you can see it's even closer, right? So that would mean even more sinking air kind of in this region. One day, there it is again. So as I go day to day, you'll see it moves around a little bit, but it's pretty much just staying in this one spot, producing sinking air. And that sinking air is going to fight cloud formation, and we have clear skies for most of the days of the winter. Now, before we change the season, let me just point out that these are mid-latitude cyclones. That's what these guys are, right? So those guys are going to come ashore, and they're going to slam into the west coast north of the Pacific subtropical high. So you can kind of think of it like the Pacific subtropical high is kind of blocking the storms from coming in, and sometimes we'll talk about that in weather reports, that the high is blocking the low. It's not quite how it works, but you can think of it that way. Okay, so now let's change from a winter day to a summer day. Okay, so same thing. I'm going to change to sea level pressure. And now that big white blob there is the Pacific subtropical high. So here we are down here. Notice how much bigger it is. I'll zoom in a little bit. So by comparison, the one we saw last time was kind of like about that big. This thing is giant. And so we saw that in the animation, that the Pacific subtropical high gets larger in the summer, in our summer, and it moves out into the Pacific Ocean away from where we live, kind of far from the coast. But notice that these winds are coming right down the west coast right here, right? So we are farther from it than we were in the winter, but these guys are actually under pretty strong influence of the Pacific subtropical high. So they are getting sinking air all the way up and down the coast. So we call this Mediterranean climate. Mediterranean climate, named from the Mediterranean Sea, is a place where you typically have wet winters and dry summers. West coast of the United States, super dry summers. If you look at, say, rain records for like San Francisco, I mean, there's like 30-year periods with no recorded precipitation in the summer. Okay, super dry because of the Pacific subtropical high. So if the ITCZ is moving, and the Hadley cells are moving, and the subtropical highs are moving, and the polar fronts are moving, what we get are moving patterns of precipitation throughout the year. So this animation is showing monthly averages of precipitation. So what they've done is for each one of these months, they've gone back 30 years and looked at all the precipitation that fell around the world and plotted it. And as you might expect, the darker blue colors mean more precipitation. So this one is in millimeters, so dark blue, 400 millimeters of precipitation for that month. Now, one of the things that you notice at first is that you've got this dark blue right through here. That's the zone of most precipitation, is following pretty closely the ITCZ. So as the ITCZ migrates north and south, this blue stripe migrates north and south with it. Okay, so a lot of rain is falling along the ITCZ. They have these gigantic cumulonimbus every day. The other thing you might notice is that we have these white areas, and white means no precipitation. So if you remember from last lecture, we talked about how the subtropical highs, in theory, would form a stripe all the way around, a band all the way around the Earth. the Earth was all the same thing, like if it was all water. But the fact that you have continents breaks that up, and you can see that here. So here's a subtropical high, here's a subtropical high, here's a subtropical high, and in between there's some wet zones, right? So it doesn't really form this continuous band because the continents kind of mess this up. But you can definitely see the effect of these subtropical highs. These are areas where it literally may not rain for weeks and weeks at a time. Now, this one in particular is the one that we are interested in. This is the Pacific subtropical high. So notice that it grows into the summer and then it shrinks again in the winter, and it migrates north and south a little bit, right? So we just saw this, but here it is growing out into the summer, out into the ocean, then kind of shrinks back. Point is, it's closer to us in the winter, even though it's smaller. Another thing you might notice overall, most of the rain falls in the ocean. Okay, you may not have thought about that before, but there's a lot of white out here in the continents because once storms leave the ocean, they don't have a source of moisture. So that rain out effect, rain shadow effect all happens. And you see big areas out here in the continents, you know, like here it is in the winter, really dry out there. Remember, cold air, dry air. So in the winter, even if you might have a really big storm, it doesn't have that much moisture. So you see really dry areas up here, say in in Canada, in the Siberia, in the winter months, it looks pretty white. They get very little precipitation. So most of the rainfall falls in the ocean. So we're going to go through month by month what the precipitation patterns are like in the United States. So each one of these maps I'm going to show you is a 30-year normal. So again, that means we've taken records for 30 years and we're going to use that record to determine the averages. The colors represent how much precipitation fell in this particular month. So in this case, this is the January. So let's look at this, and we're going to concentrate on different areas of the country at a time. And let's look at the West Coast here. So we've got a lot of precipitation hitting the West Coast. Those are those mid-latitude cyclones coming in, right? If you can see, once they pass through, now the colors indicate a lot less precipitation. That's our rain shadow effect. And then they pass over here and really dry, and we talked about this last time, how they have gone over these mountains and they go through the Rockies and then they come down this eastern slope and there's not much precipitation left and the air is going downhill, and all those things fight storm formation. So we also said last time that once you get a low pressure center out here, the mid-latitude cyclones come through this way, they can pick up more moisture and they're re-energized and they produce more precipitation. So you see a lot of precipitation down here also in January, and that's mostly from these mid-latitude cyclones that they run out of gas down here, but then they pick it up again over there. Also, significant amount of precipitation up here in the northeast. Okay, so we see a pattern that's very similar to that. We go to February, and notice what happens as I move into March and then April. I start to see that the wet area is shrinking towards the north on the west coast, and that's because our mid-latitude cyclones are moving further and further to the north until eventually we get to June and then July, and there's basically no precipitation along the west coast. And the other thing that's happening is that Pacific subtropical high that has set up shop out here, and the sinking air is providing for a very dry coast along the west here. Okay, so let's back up and talk about what's happening in our part of the world. So in our part of the world, we're downstream of mid-latitude cyclones. They come ashore here and they come inland, and maybe they dump some more precipitation, but by the time they get to us, it's pretty dry, right? So we're in the kind of the rain shadow of this whole area. And so we have a pretty dry January and February and March and April, and we can see the effects of that Pacific subtropical high keeping this whole area pretty dry. And then here we are in May, and the east half of New Mexico is actually starting to get some precipitation because we're starting to set up that unstable air that we call tornado alley. We've got warm, humid air moving in from the Gulf of Mexico. We occasionally get cold, dry air coming down from Canada. They mix it up over here and produce lots of thunderstorms. We're seeing that kick off here, and eastern New Mexico is getting a little bit of that. Now, the mountains right through here block that moist air from coming in. So this pool of dry air is protected from this humid air from the mountains. Okay, so that's May. June, kind of the same story. And then, boom, July, something changes, right? And what happens is we get our monsoon circulation. That's the next lecture. Okay, so I'm going to just punt on that for now. But we go through our monsoon season, and then the monsoon season kind of comes to an end, and we start to see the rebuilding of that Pacific subtropical high, the effects, the dryness here, and then we get into the winter months. So we're actually finally getting into this book a little bit, and we're going to get more into this book in a couple weeks, but there's a few pages that apply to us now. So in the introduction, pages 10 and 11, there's a section here on the difference between weather and climate. Okay, so we kind of talked about that. They talk about climate zones, and there's a map of the world, the major climate zones of the world. So based on everything we've talked about, right, the ITCZ, subtropical highs, polar front, all that stuff, there are zones in the world that have similar climates, and they get names if we're into this. We're not going to dig that deep. But this map kind of shows some of the different climate zones that are set up because of some of the things we've been talking about. On the next page, so here it talks about layers of the atmosphere and composition. We talked about that in the past. The last lecture was on atmospheric circulation. There's a section here in the book that has a breakaway view of the circulations that we were talking about and some basic principles of circulation over here. So it's a good kind of review of what we talked about last time.